All right. Hello again. Welcome to the Data Science Seminar from the University of Washington eScience Institute. This is our last seminar of the quarter. Thank you for joining us today. Dr. Elham Khoda, who's a postdoctoral researcher in the Elementary Particle Experiment Group, working with Professor Shi-Che Su. Elham completed his PhD in particle physics at the University of British Columbia, Vancouver, Canada. And during his postdoc work, he was further interested in developing machine learning algorithms to solve particle physics challenges. He's a major contributor to the group activities toward data-driven discovery with accelerated AI algorithms. Today, he will talk about this very topic, really how to run fast machine learning for particle physics applications. As usual, please use the Q&A button at the bottom of the screen to ask Elham any questions you may have. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. And with that, Elham, I'll hand it over to you.
Yeah, thanks, Nicoletta, for the introduction. Yeah, firstly, I just wanted to thank the Science Institute for inviting me for this giving the talk. And yeah, so this is my pleasure, to be here today and talk about the fast machine learning inference on FPGAs for particle physics applications. Just to start with, a little bit of introduction of myself. I'm a postdoc at the University of Washington, and I'm mostly working on the particle physics experiment called ATLAS, and working with Professor Shi-Che Su, and also part of this NSF A33 Institute, where we have some sort of multidisciplinary collaboration. And right now I'm visiting LBNL, the Berkeley lab, as a postdoc affiliate. So right now I'm at Berkeley. I finished my PhD from UBC, and I also was working in particle physics when I was in my PhD. So this work is more sort of related to the particle physics experiment. And the experiment that I'm part of is the ATLAS experiment, which is one of the experiments on the Large Hadron Collider. And what is the Large Hadron Collider? It's one of the world's largest and most powerful particle collider. It's on the Switzerland and France border, underground, and it's a big ring, and there are 4 major experiments on that ring, and ATLAS is one of the major ones. This experiment, the Large Hadron Collider, it's a collider, so it collides proton bunches of the order of 10 to the power 11 proton bunches, spaced by 25 nanoseconds. You can think about like a very highly squeezed proton bunches getting collided very frequently, basically. And these experiments, these are covering, there are beams coming from opposite direction, they're colliding each other, and these experiments kind of cover the collision point and detect whatever comes out. The energy of these beams that collide protons keeps changing, or rather keeps increasing over time. Right now, we're in this stage 2022 to 2025, where it's almost close to the target energy that was designed this experiment for. And I'll talk about some part of current era, and mostly the work that I'll highlight will be more relevant for the future upgrade of the same experiment. It's called high luminosity LHC. So there, it's expected to collide even more proton bunches, meaning like in more density. That will start in sometime later. As of now, the expectation is to be started around 2028 or so. But regardless, this work is super crucial. This kind of work is crucial to get done right now. So with that, I'll just move and say, like, the ATLAS experiment, it's a big experiment, it's a big detector, which is on the beamline. And naively, you could just think, this detector is a multi-layered detector. So it has multiple layers of sub-detectors, and those sub-detectors are of different type. And they also do different type of tasks during the experiment. So basically just highlighting at the very outside, there will be muon spectrometer. These kind of detectors are designed to detect the particle called muon. Then there are some calorimeters inside, which usually measure the energy. There are a few types of them, like a few types of detector technology. And then we also have this inner detector, this core of it, and is called inner detector. These are all silicon type sensors. And these are, there are also like a few different types of detectors, sub-detectors inside this inner detector. So in a nutshell, like there are different types of detection technology used to detect the particles that's coming out of this collision process. We're colliding protons, right? And whatever comes out, we are detecting through, passes through this detector, and then we're detecting using different detection technology and different properties of the particles coming out. So usually, like this is a cartoon diagram. It shows the detector in cross-section view. This is, let's say, this is the collision point, and protons collide, something gets produced, and that thing travels through the detector. And depending on the property, it will react differently or interact differently in the subdetectors. Like the charged particle will have some response in an inner detector, where we call this like tracking type detection. You just try to collect the charge and make a track out of it. Then some of them will also deposit their energy in this calorimeter detector. Muons are very, they don't interact too much, so they pass through all the way up, and then they detect, they interact a little bit in the tracking. So we'll have some tracks, and we'll also have some tracks in the muon spectrometer. So yeah, so this is kind of the idea, like as the particle goes through the detector, they will interact, and based on the interact, we'll try to reconstruct them based on the detector responses. And then eventually, this I'll highlight, and we will also even try to identify them. Like by looking at the detector response, you need to identify what type of particle that could be. Yeah, so now I'll be back again to the Atlas experiment, how the data gets collected. So regarding the phase 2 upgrade, that's the upgrade I mentioned at the beginning, which is going to happen in 2028 or so. The whole some of these numbers are based on that. So the way it works, the protons are getting collided with very high frequency. So the frequency is roughly 40 megahertz. And so basically millions of protons getting collided in a second. And it's very difficult to detect, it's very difficult to read out the collision at that high rate. So as a result, what we do is that we filter out some of those. The way we do that, like it's a 40 megahertz frequency, and we filter out to roughly one megahertz, so 40 times less. And then the idea is that we look at those collision events and very quickly decide whether this looks interesting enough or not. And so that first level of selection is called level 0. That usually happens on a hardware. Hardware meaning it could be a chip, it could be some FPGA, that's field programmable gate arrays, also some sort of electronic device. I'll talk about that shortly. But it happens on a hardware. Since it's a very high frequency events are happening, we don't really have much time to think about. So we have to make a decision in order of microsecond. And then there is another stage, which we call event filtering, where we have a little bit more time. We have roughly orders of hundreds of milliseconds. And there we can actually do some sort of more complex algorithm. This is again another level of selection. So, the prevents that goes through from this part, we get another chance to sort of look through them and decide whether, okay, this looks interesting enough to just store them for offline analysis later on. We often use some sort of machine learning algorithms like BTTs, boosted decision trees, and neural networks. But now time has come where people have started exploring more advanced ones at this stage. And there is another stage when we also we kind of decided these events are interesting. We just all store them. We read them out. We store them, and there is no time limit as such. We just get to, those data are all stored. We get to access them and do our studies as we want. And then majority of the machine learning applications or algorithms are being run on that during this stage in experiments like Atlas experiment that like ours and other similar experiments the CMS experiment at LHC, where we do any sort of general purpose studies of particle physics. So the offline, this, as I mentioned, this is mostly complicated ML algorithms are being used, and also this is a place where most of the R&D and improvements of machine learning happens. But then less conventional part is the triggering part. We call it trigger. This two-level selection, we call it trigger. Level 0 trigger and eval filter. It's because of the latency requirement, because we have records of milliseconds, first microseconds and milliseconds. It's very difficult to do any sort of a complex task there. But as we go moving ahead, there is a chance that we could do, people have started thinking about whether we could use any machine learning algorithms here at level 0 on hardware. The only problem is that it has to be run on a hardware if it's a machine learning algorithm. So now the question is how to run a neural network inference quickly on an FPGA. FPGA is one of the hardware, or let's say on a chip, ASIC. So first, just to bring everyone on the same footing, I would just go over very briefly what is an FPGA, and just so that we are all on the same page. And then we talk about more how we run or implement a machine learning algorithm on an FPGA. So FPGAs are field programmable gate arrays, which is basically a reprogrammable integrated circuit. Here in the right-hand side, this is a cartoon diagram, which shows different components of the FPGA. So the FPGAs contain different building blocks. We naively will refer them as resources. So when you will hear resources later in this talk, you just remember that this is one of the components of the FPGA. Now, originally, the FPGAs were popular for prototyping ASICs. Those are the integrated circuit chips. But then nowadays, it's also being used for high performance computing because they're very fast and we can do like highly parallel computation if we configure things properly. The major building blocks that we'll highlight are the multiplier units, which will be shown in one of these green boxes, and then some other things like lookup tables and flip-flops, some of these orange boxes, and then also the RAMs on the chip is BRAM. Block RAM is also shown in a green box. So very quickly, why FPGAs are good and important. They can actually run at an extremely high frequency, so order of hundreds of megahertz, and you can compute outputs in an order of nanosecond. Usually FPGAs are usually we use high-level programming language, hardware description language people call Verilog or VHDL. But nowadays, it's also possible to write your code in C or C++, and then there are compilers or two from different vendors like Xilinx, Intel. They can take your C++ type code and then compile them and produce this kind of code, Verilog or VHDL, the hardware description language code, which the hardware then understands. So we call these tools as high-level synthesis HLS tools. Our work will be mostly concentrated around these HLS tools. So first, let's just quickly highlight the DSPs. These called digital signal processors. These are specialized units on the hardware, which are used for multiplication and arithmetic. So in a neural network, mostly the neural network type of machine learning algorithms, you'll do lots of multiplications, like mostly matrix multiplications. And these matrix multiplications could be done very easily if you configure it, optimize it properly with these digital signal processors, in short, DSPs. So these are basically specialized units for multiplications or arithmetic. We often call them also multipliers. These are much faster and more efficient compared to the other units like these lookup tables. Lookup tables are, these are logic cells, and these can also be used for small arithmetic operations like small number, small Boolean operations like addition, subtraction, addition mostly, and also it could be used for small memories. These lookup tables. Another type of resources that we often use are called flip-flops. They control the flow of data with a clock pulse, and this kind of hardware usually have a clock pulse. But then the way to think about, we have in a neural network, we have like states going from one layer to the other. So that kind of workflow, like a data flow, you can think about could be mostly done or maintained by these flip-flops. Okay, so with that, I'll just quickly go through this neural network computation, and then try to correlate with the hardware that we talked. Most of you are probably already quite familiar with this very simple description. But just to quickly explain again, for a layer M, if the state is xm, the way we get it, from the previous layer m-1, is that we do this multiplication of metrics, which takes the inputs from m-1th layer to the mth layer, so that this W matrix. And then we multiply that with this the state before, x of m-1, and then we add the bias term. So this is a weight times the state before plus the bias term. So that passed through an activation function that essentially gives you the values in this of xm. So that's the basic inference computation when you run a neural network, the dense neural network or normal neural network. Now think about like what we just discussed in the 2 slides back. So we have on an FPGA, we have an unit called digital signal processor. Those are multiplier units, and here you can see we are doing multiplication of this W's. The weights are getting multiplied with the states, and also some additions. So the multipliers are pretty good for doing this kind of should be like very efficient for doing this kind of stuff. So that's the first part of it. So we need to basically do that part on the multiplier. And then the another part is just a functional call. Once you do this multiplication and addition, there is a functional call that takes this number and then computes another thing. It could be done many different ways, depending on what we are doing. It could be done on a lookup table. It could be also done on flip-flops for simple ones. And it could be also done on as a memory, like a BRAM. So there are a few different type of implementations possible here. So that's pretty much what we do here. But yeah, first, now moving on, I will just quickly highlight the whole workflow that usually, for this kind of task we take. So we are using this tool called high-level synthesis with machine learning algorithm for high-level synthesis for machine learning HLS for ML. Package. That's an open source package developed by us, our collaborators, and mostly used in particle physics domain currently as of now, with some applications in other domains like Astro and nowadays we are also working on neuroscience. But the whole idea here is that you have a model, you train it with your best software, Keras TensorFlow or PyTorch or something else, and Onyx, you can convert them to the Onyx format. So you have a model in one of these formats. Then once you have this model, this tool can take that model. It can convert your Python-based model from the Python-based tools to the first high-level synthesis conversion. That's HLS conversion. So it'll basically read through all the layers, all the information inside the model file, try to interpret them, write a similar C++ code. So this is the part we need to implement whenever we try to implement a new model. So this is the part we need to implement in this tool. Once this is implemented as a user, you can always use it. But then first time, as developers, we need to always implement that. And once you have these HLS converted tools, there are compilers like from Xilinx tool. There's a Vivado HLS. There's from Intel. There's other HLS compiler. These compilers help to compile this tool and optimize this tool. So optimize this interlearn representation we call. So from Python to C++, this representation can be compiled and optimized with these kind of compilers. So once you have some internal representation, you can always convert it in an HLS project, fine tune it based on how fast you want it to be executed, how much resources like TSPs and flip-flops it's taken, whether you can do something smarter so that it takes up less part of the board and also executes it faster. So you do this kind of optimization, and when you are happy, you try to convert them to this this hardware description language using another tool called this actual Vivado compiler, or another Intel compiler. This is a different one. So there's two stages of conversion. You have this Python to C++, optimize that, and then once you have C++, you again convert that to the hardware description language and optimize that. There are two stages of optimization and conversion, and this can be all coordinated with this HS4ML package, because this kind of interfaces with these compilers and gives you handle to optimize and fine tune. And once you have this hardware description language, you're happy with the with the optimized version of it. You then will be able to run it on an FPGA on hardware. So whatever model you train here will be running on the circuit. So it'll be then you can pass data, you get output out of it. So this HS4ML software tool it's mostly implemented for neural networks on FPGA, and it supports many different common layers like DNNs, TNNs, and all sort of other common ones. The recursive neural network were not implemented until late 2022. So one of the projects I'll highlight in this talk will be implementation of this RNN-based architecture. This RNN-based architecture for our back to particle physics again, the triggering and level selection we talked, could be used in level 0 in that sense. We have some particle called tau particle. We can, these are all examples, like one can use an algorithm, one can implement an algorithm which can identify tau particles at the trigger level selection. And also there are some other type of energy regression, like missing transverse energy reconstruction could be done in particle physics experiments using this kind of sequential algorithms. So I can stop here very momentarily, just to see if people have any concerns, questions, or any other things. Just to give you a little bit of time to think and ask questions, and then I'll continue. So I'll pause for a bit here. If you have any questions, you can type it. Okay, as of now, I don't see any questions popped up in the Q&A box, but yeah, feel free to write during the talk. Whenever you get confused or got lost, we can always stop and clarify those before moving on. So I will move on to now some applications that we did. So before that, I'll just quickly highlight about define and show you what a particle jet is. So we're colliding these particles, protons, and out of the collision, there will be lots of things produced. And then as they go, there's lots of radiation happens, depending on what type of particle they are. So the quark, mostly the quarks, there are 6 different type of them, and gluons. Those are like different particle name jargons. But these kind of particles, fundamental particles, if they get produced, which they often do, they will do lots of radiations. And then because of the radiation, they're often very close and collimated. What happens is that you end up seeing a sprayer particle going through the detector, basically. So you collide, the particles travel, as they get produced, they actually radiate a lot. And then by the time they hit the detector, this is some schematic of the detector. By the time they hit the detector, they will be a sprayer particle. So that particle, sprayer particle, we call basically jet. And as a result, this is one particle, but then we observe in a detector, we observe a little bit far from the collision point, we observe a large energy deposition in one of the calorimeter type detectors. And if this particle is a charged particle, we'll also see some ionization in the initial silicon type detectors. So this is basically jet. Now we'll talk about jets and then different type of jets. Now, depending on where they're coming from, which type of particle is the original particle, the type of and the how the jets look, they're very different. So in principle, you can by using the information and from the detector, you can identify them. So we are using machine learning for jet classification here. Depending on where the jets are coming from, whether up or down or strange or charm, different. I'm just talking about different type of jet names. Depending on where they're coming from, they might look slightly different, and these could be all probed using the information that we read out from the detector. Perhaps, and like the example I'm going to show, perhaps it's not very realistic for a trigger system, but this essentially it shows you that if we have some sort of machine learning algorithm, how that we can implement them on the FPGA and how the whole thing looks like on an FPGA. So here, in this example problem, what we're doing is that we have 5 class classifier. So we are having 5 different type of jets, particle collections basically. We call them top type jet, Z type jets, W. These are all particle names, and other quarks other than top, and then gluon. So these are 5 different types of jets. They look very different. And we're using these variables. You don't need to know all these definitions of these variables, but then the way these variables are essentially gives you information of the energy deposit that you have in calorimeter, how they look like. If you look at the energy deposition, from the top, whether they are continuous, whether they have some blobs inside it, some information from the interior part of the detector, whether there is some you see here, there's this little bit of discontinuity. This kind of information are encoded in these variables. Some of the distributions are also shown here, and you kind of see like different colors are different classes here, and you kind of see here, and the different classes are often different looking depending on which variable we're choosing. So this is a multi-class classifier on a deep neural network trained with these variables, and these plots, ROC plots shows you the signal efficiency on the x-axis and background efficiency in the y-axis. So we want this background efficiency to be as small as possible, so close to 0 basically, and the signal efficiency should be close to 1. So we want basically at this point like somewhere here. So like very high signal efficiency, let's say around 90%, and this to be the y-axis to be like as small as possible. So you can kind of see here, and around 90%, it's less than it's like 0.5 or like 0.2, 0.3 kind of background efficiency. So we still have very high signal acceptance and low background efficiency. And all of these different lines are different performance of different classification tasks that we're doing. We have 5 different classes here. So 5 class classifier it is. And all of them, this area under this curve is more than 90%. The area under this curve, if it's 100%, then ideally it's a kind of close, nearly perfect classifier. In this case, it's all 90%, so they're pretty good. So means like we have an algorithm. I'm not talking about the details of the model. I'm showing you like some of the inputs. So we have some inputs. We have an algorithm which mostly works. And now the question is how we want to implement them on an FPGA, right? And what are the things that to optimize? The first thing we need to think about that I want to introduce is this quantization method process. This quantization is reducing the precision of the neural network in an arithmetic. So once you have a trained neural network, what you have at the end of the day is you have some weights like a matrix and bias, a vector. You have those weights and matrices, and then you have some inputs. You basically need to do a transformation. So you multiply those weights matrices, and so you do like lots of multiplication and with some functional call, like I mentioned at the beginning. Now, when you train your model in a Python tool like TensorFlow, PyTorch, or whatever you use, often you store your elements in the matrix, the weight matrix, in a floating point number. So that's most likely is going to be 32-bit numbers. Now, 32-bit numbers are pretty huge, and we don't really need that much precision to run them on an FPGA. And it's basically useless. Also, like waste of resources on an FPGA. You don't need to have that precise value there. So this process of quantization is reducing the bit precision. So we want to reduce the bit precision until we don't start to lose performance too much. So HLS for ML uses the fixed point representation the way it is shown, it is if you have a number, integer part plus the fractional part, the way it is done, like both the integer and the fractional part are converted into binary representation. And you can see here in this cartoon, this is the integral part, and this is the fractional part. And the way this AP fixed numbers, the HLS4ML uses is denoted is the total bits, comma, it's a tuple notation, total bits, comma, the integer part of it. And then the whole thing is called weight. So for example, here, we had this model trained before in slide number 23, where we are showing the plots trained with Keras TensorFlow. Now we did quantization. We adjusted the precisions 16,6, as I mentioned, is total weight, integer plus fraction, comma, integer. So 16 here is like 6 integer bits and 10 fractional bits, and total 16. So we did some adjustments. These are not 32 bits anymore. We did some adjustments, and as you could see on this plot again, the solid lines now are the same plot that you saw 2 slides back, and then there are some dotted lines overlaid on this plot in the same color. They represent the same classifier. It's very hard to distinguish between the solid and dotted. It's a log scale here. There are some parts in the bottom, you can kind of see the difference between the red dotted and red solid, and also like purple dotted and solid. But other than that, most of it is very, very much indistinguishable. So that means that when we adjust our weights based on this 16,6 precision, changing the integers to 6 and fractions to 10 bits from 32, we don't really see any performance drop. So this is a good number. Now, the question is, this method we call post-training quantization. So we have a trained model, we have the weight matrix, we're quantizing the weights after the training. Now, the question is, how do you decide what to use, right? 16,6 or something else. So the way we do it, we scan through the few numbers, we fix one of them. So we fix, let's say here, in this case, we fix the fractional bits to 8, and we scan the integer part of it. So the fractional part is fixed to 8, and the integer part has been scanned starting from 2 to all the way 32, right? And you calculate the area under the curve. So that's the area under these rock curves in both dotted and solid. So you take the ratio of them. So the FPGA AUC is the adjusted number, and then expected AUC is what you expect from in your initial model from PyTorch or TensorFlow, and take the ratio. So if they're identical, if you don't see any performance drop, this number should be 1, right? But if you start reducing this precision too much, then you will see the effect. That's what you see here. Like with the 2 integer bit, you see like the ratios are pretty bad, like 0.6, 0.7, 0.8. Up to a certain point, like when the integer bit is 6, you actually see like almost 100%. And even if you keep on increasing it further, it doesn't really improve anything. It stays on like 100%. So this might as well just cut here. Like there's no point of, like there's no additional advantage of using a 10 integer bit compared to 6 integer bit, for example. Similarly, you do another scan in the other side. So you fix the integer bit and you scan over the fractional bit now. And you again find an optimal point where it's a good enough to cut off. So that way we first step is to find the optimal precision based on these scans. Okay, so once you do this, find these optimal points, you do the next steps. But before I go to the next steps, I would just quickly highlight here. The method we just talked is the post-training quantization. So you have the trained model, and then you have the everything. With this HLS4ML tool, you do post-training quantization. You adjust the weights and biases, and then after that you do the HLS conversion, which I'll show some results in the next slides. Another strategy could be that you have your initial model, which you either defined on TensorFlow Keras or you define on PyTorch, and then you do a quantization aware training. So you have a base model with this fully Python tool, and then you want to do a quantization aware training. So you define the same model slightly differently with a quantizer inbuilt to it, using tools like QKeras, the quantized version of Keras, PyTorch. It has also the inbuilt PyTorch. The native PyTorch has some capacity of doing it. TensorFlow also have some capacity nowadays, but very limited options. You can't really do a scanning. There are only 2 or 3 options, choices you can make. And there's a tool called Quantize Onyx. Onyx is a neural network format, model format, and Quantize Onyx it's in development. So these kind of tools one can use, and the idea here is that you do the network training again, including the fact that these weights are going to get quantized. So you are basically simulating that kind of situation while training. So the network gets chance to adjust the weights and everything based on that approximation and that consideration in the future. So that essentially is very I would say very very smart, and it usually gives you much lower bit widths. You get similar performance because you are optimizing that while you're doing the training. And once you have this optimized model, you are going to do the HLS conversion. So now I would just highlight another example model that we worked on lately with this recurrent neural network. So very quickly, RNNs. RNNs, I think many of you might be familiar. These are very good for design for sequential data, so like text, audio, video, like strokes, like sketch, like sketch diagrams basically. And RNNs have a state. The naive idea is that RNNs have a state at each time step, so it's updated at each time step as a sequence process. So you can think about the text. You have like let's say characters. So or let's say if you're learning the words, for each word the state would be updated as you go through the sentence. So it's that kind of idea. There's a sequential notion to use, and it has a recurrence relation at each time step. So this state is a function of weights. It takes the input at that state, and it takes the state from the previous time step. So basically, each state is a function of the current input and previous state. And the previous state you can think about is kind of a memory notion. There is a memory notion to it. And the output would be, again, a function of the current state and the previous, current input and the previous state, or you can call it past memory. So this is the recurrence relation. Every time stamp, you just keep updating. And if you think about it completely unrolled, meaning, if you think all the time sequence one by one, so you have like the X is like X0, X1, X2, and go and so forth. X0 goes in, you get Y0 hat out. You have this H0 calculated based on H0 and some initial number. And then based on the H0 and X1, it will calculate H1 and some output, and it keeps going until you have the sequence. That's kind of the idea here. And this H states, the idea here is that the sequence when it's processing second input, it will still have some idea about what X0 and X1 was through this H1 state. So that's kind of the memory. And there are two different types of implementation of RNNs. Those are very popular nowadays, called LSTMs, which is long short-term memory, and then graded recurrent units GRU. So very naively, the idea is that LSTMs has like more states, 2 states and 3 gates inside it. GRUs has 1 state and two gates. So essentially, very naively, you can think about, since they have more components into it, the gates and states, it has more matrix multiplication compared to the graded recurrent unit. So graded GRUs are easier to do, like faster to train, also faster to do inference on. Now, you don't need to think about too much about the equations, but then roughly just look at the structure of the equations. I'm just taking an example here at the gated recurrent unit, GRU. Yeah, there are multiple equations involved in this whole computation as we go. If you look at these highlights, these are essentially the sum weight matrix multiplied by some vector plus some another vector. So this is essentially what you do in a dense layer. Similarly, there's another matrix multiplied with another state, another vector basically. So you have matrix times vector plus some vector, another matrix times vector. So all these components that are involved in these kind of RNNs are essentially the smaller. If you split them up in smaller chunks, these are all what we do in this dense neural network. So when we were implementing them on FPGA, this Python to C conversion tool, we took the idea from that, and then we basically essentially used lots of implementation for a native dense environment, dense layer usually do. Again, this dense layer has these kind of things, and often these multiplications will be done on multipliers. So all of these would be handled by multipliers, and then we have the sigmoid function, which could be done on mostly on the lookup tables. 10H also on lookup tables or flip-flops basically here. So by reusing all the components that we often do for simpler dense and architecture, we can essentially do all this recurrent layer implementation. Recurrent layer has this is a loop, a recurrence relation, as I mentioned here. This is a loop over the time step. So we need to do that thing many, many times. That's the memory consuming things. We need to keep track of. We need to do things like in a multiple times. So it ends up using lots of resources on the board. But otherwise, it's very similar to the dense. Now, to test our implementation, what we did, we picked the 3 benchmark problems from particle physics and some general problem. From particle physics, we took again this gender identification. So we have a binary classifier which identifies between this top type jet and other type of jets. And there's a 3-class classifier which identifies this B and C type of jets and light. So there's a 3-class classifier. And there's another 5-class classifier which identifies all these sketch diagrams. So we basically filtered 5 different type of diagrams out of them. This is from public quick draw dataset from Google. These are like a series of strokes of 100 strokes, basically clipper type of diagram. And with this series of 100 strokes, you are making all of these sketches. And the task is that, by looking at this 100 strokes, you need to identify whether these are bees, butterflies, mosquitoes, snails, or ants. Those are the 5 different classes we use in our days. The reason behind choosing these 5 different type of models are, the size of the parameters you see, like the 4,000, 60,000, more than 100,000. So the idea was that we want to test small to medium to large models and test them and the robustness of our implementation. Just to show, all these models are trained with Keras TensorFlow, and these models mostly work, the area under the curves. These are, again, this efficiency versus background, signal efficiency versus background efficiency y-axis. They all show pretty good, good to okay-ish performance. This 90%, 75%, 93%. These are pretty good in terms of benchmark. And just to remind you again, the weights and biases are represented by 32 bits floating point numbers here. So once I do the quantization, like I explained before, we look at the plots. In the y-axis again is the AUC from the floating point. AUC from this HLS conversion after quantization versus AUC in the Keras, the original models. We take a ratio and plot it here. Is it the LSTM? Those are the solid lines. Those are pretty close to 1. But GRU, there was some technical reason we got to we stopped around 95%-ish saturated there for this particular model, a small model. And the medium model in the middle, you see there are all of these lines, they all saturate around close to 1. For the large model, the red lines are saturating close to 1. Red and I think green is also hiding behind. So red and greens are saturating 1, and orange and blue are below 1, the y-axis. And different colors are different integer bits. That's the first part of the integer part. How many bits you're using to represent your integer part. The x-axis are the x-axis are the fractional bits. So by looking at these plots, you can kind of understand that around 10 fractional bits, all of these models are pretty good. And the integer bits depend on size of the model. The small model, 6 is fine. The medium model, probably 6 or 8. And the large, we probably need 10 or 12 are good. So we picked those numbers based on these plots. And then what we did is that we implemented them on an FPGA and optimized them. So here I'll introduce another concept. It's called how we do parallelization on an FPGA. So take a very simple example here. The example is that we have a 2-to-2 transformation. You have 4 different type of multiplication we're doing. One way we can do all 4 multiplications in parallel, fully parallel. We call it reduced factor of 1. So we are using multiplier just 1 time. We're not. Another extreme case would be using 1 multiplier 4 times. So doing sequentially, that's the reduced factor of 4. If you do that, you are doing fully serial, you're using less resource because you just keep using the same thing multiple times. So high reduced factor. but you have very high, so very low resource utilization, but very high latency because you are waiting basically 4 times. It's taking 4 times compared to this. So this is fully parallel. It's very fast because it's just one go, you're doing 4 different multiplications, but it's again taking lots of resources, 4 different multipliers. Now, this is a very simple example, but if you have a large model like we had in an RNN, you keep multiplying in a loop, you have to be careful, and you have to find a trade-off between this, fully latency dominated, like a high latency and fully serial kind of situation. So here, the example, again, back to the jet classification problem we did in the very beginning, the 5+ classifier. You can see here, we have the reuse factor of 1, which uses a very little, like the most of the, this is like an order of 5,000 DSPs they're using with this precision. But then as you lower the reuse factor, increase the reuse factor, meaning you keep using the multiply units 6 times, let's say here, and those are these lines here at the bottom, it uses very little compared to 5 times less, basically. Similarly, if you look at the time, now these numbers, the reuse factor 6, those brown numbers are at the top, it's taking lots of time compared to almost like more than double, 2.5 times more compared to what you do with the reuse factor 1. So we need to find, a middle, kind of a middle point based on our requirements and needs. For now, again, back to the RNN model that we just worked out and explained. This is the actual thing we published. We tested many different type of reuse factor, and then most of our case, like which is total width of 10 plus 8 or 6. So 18 roughly, you see like most of these are within the limit. These horizontal dotted lines are the limits, like that's many units. These are all multiplier units, the DSPs. That's many DSPs are on the board, so you can't really use more than that. So, so you see like, for the regime where we are interested at, or where we saw our models performing very good, the precision, 18 total with roughly 10, 6 to 8 and integer bit, and 10 fractional bits. So 8, 18 or 16, they're all good. They're all fit, like we can all implement them on the board. And for your information, in case you are interested, we are using this particular board, FPGA, from Xilinx. Okay. So now, just to summarize this part, some of the most challenging problems in high energy physics exist in the trigger. That's the high level, selection process on the fly, and machine learning on an FPGA is very crucial in order to do that very quickly. And HLS for ML is a user-friendly inference interface for Python model to HLS conversion, high-level synthesis language conversion, which you can implement on FPGA. I have shown that RNN-based models could be good performance at trigger level, and we have shown the implementation, proof of concept of the plots, and the papers are all out. You can have a look. But then the question is, what's next? Now, the transformers, you might have heard many of them. All this language model nowadays people are using, the core of it is the transformer model. I'm not going to go in too much details of transformers. I just have one more slide just to highlight that this is another work that we're mostly finishing now. The transformers, the core of it is that it has a attention mechanism, which I'm not going to explain, but I would just tell, it involves lots of matrix multiplications. So we have this V, K, Q, these are all large square matrix kind of architecture. These matrices will be all multiplied. So there are lots of huge matrix multiplication inside happening when you train a transformer, as well as after training, when you do inference, meaning when you evaluate the model, there is also like a huge multiplications you need to do. So it involves large matrix multiplications. It's a bit tricky to implement on an FPGA board, and also have a very low latency, meaning you run them very fast. We have tested in one of our model, the B-tagging model, the one I just explained in the context of RNN. It's a 3-class classifier identifying jets, whether it's coming from B type, C type, or light type. And we have roughly 10,000 parameters at the moment. It's performing pretty good. And we implemented it on an FPGA. We get a latency of 2 to 3 microseconds. So it's very good, because we need the microsecond latency in order to use them on our hardware trigger in particle physics experiments. But more realistic and get the more benefit out of it, LIGO, the gravitational wave experiments, they also have time series data. And there the latency requirements in milliseconds or sometimes seconds. So we get more time there to run an algorithm. So I think we could exploit the the advantage of transformer models for those kind of data sets. So we have started working on LIGO gravitational wave experiment data set. Mostly simulate most of the part is a simulated data set. So we're training a classifier which identifies signal relation background using a transformer architecture. We have also that work is mostly finished and we're wrapping up. And we are also working on in a completely different application domain, whereas neuroscience, we're detecting the brain activity. So in the brain we have neurons, and the neurons fire very frequently, and there are labs in UW who does experiment with them. So we're taking the data. These are all time series data. They're just collecting the neural firing data, and the spiking data basically. And by looking at those spikes, we are trying to identify the neuron activities. These are again time series data. And the idea here would be, when you can use this if you are able to implement this kind of methods on a circuit, electronic circuit, FPGA or a chip. The advantage would be like you can have something inject, some detector or some electrode in your brain. You can collect data on the fly, and you can just decode them very quickly on the fly, and you can do whatever the brain wants to do. So for a real life example, for example, if there is a patient who is paralyzed and they don't want to, they can't move their arms or something. If you can detect their brain activities and then info what's that is on real time, you can actually do the work for them with some external device. So that would be pretty cool, and we're still working on it. And this is in work in progress stage. So yeah, so that's mostly it. And I just wanted to thank, and I'll stop here. Let me know if you have questions, comments, and I'll be happy to discuss more.
All right, thank you so much, Elham. That was a really nice presentation, and I enjoyed all the details. And it's interesting to see how the different types of neural networks you have to find the proper precision for all of them. And I wanted to ask you this question, but you answered it during your talk. For example, from a very practical point of view, if somebody's new to this, where would they start? Like, where are some resources? Like, where are the systems? How can we learn more?
Yeah, so I know the application domain is one thing. Like if it's a LIGO data or like some neuro data, so that's a little bit of expertise is required. So usually we work with someone who understands the data from that part. So that's there. That's there. So understanding the data part, and then the machine learning part is normal. So that's just normal machine learning. You can just read up from online resources. For the hardware part, then a little bit of knowledge of FPGA is required, and there are online courses as well. And there are also some of the vendors tools. So for example, we're using AMD Xilinx FPGAs. Do they have their online documents? Those are useful resources sometimes just to understand the functionality, how different things work, how you will think, in matrix multiplication, how we would think to do on the hardware. Often, I think I found some of the courses in UW are pretty useful from the ECE, like the third year or second year courses. And then for the HLS for ML tool, it's an open source tool, and we have lots of tutorials. And so if you don't want to use them, if you don't want to do like lots of development, if you just want to use them as an application, as an user for your own application, I think we have a few tutorial notebooks which are pretty good and nicely explained. And we also run tutorials often here and there, just to demonstrate how you, given a model, how you do whole thing, some notebooks, and we work through together. So those are very useful resources as well.
Excellent. Well, I'm hoping that somebody will be curious to try them. And if you have questions, please don't hesitate to contact Elham. I don't see other questions today, so I would like to thank you very much for your participation on our seminar series. We'll end our quarter here. Perhaps I'm pretty sure that we will return in person next year, and I'm hoping to actually see you in person there. We will still be recording our seminars, and we'll have the public Zoom link available. But returning in person is very likely at this point. So thank you very much for your presence today, and thank you, Elham, and we'll see you next year. Have a good
Thank you very
summer
much.
and good luck on your exams.